Have you ever wondered how drones stabilize themselves and follow given paths accurately, rockets land upright, or robots move so smoothly? Behind many of these systems is a powerful control method called Linear Quadratic Regulator, or LQR. Today, we're going to see what the LQR is, why it works so well, the math behind it, and also how it's used in real systems. By the end of this video, you'll understand how the LQR works, why it works, and also why it's so widely used in the resolution of such engineering problems. We start with the linear time invariant system, which has the following well-known form. We should specify that the LQR control can more generally be applied to linear time invariant systems. In that case, however, some things will change. But in this video we will not see this case. In the equation we are showing, x represents the state vector, u represents the control input, a is the matrix that defines the dynamics, and b is the matrix that describes how the control influences the system. Our objective is to drive the state to the origin efficiently, smoothly, and robustly. Now, these words, we haven't defined them yet. In particular, we need to define what efficiently means. With respect to the other control methods, in fact, the LQR allows us not only to stabilize, in the case the system is controllable, but also to do it efficiently with respect to a user-defined cost function. LQR defines optimality using a quadratic performance index, which is represented by the following integral functional. It is the integral from 0 to infinity of the following quadratic term, which is given by the transpose of the state vector x times the matrix Q, which is by definition symmetric positive semi-definite, times x, plus the transpose of the control input u, which is a vector, times a matrix R, which we require to be symmetric positive definite. And we will see that this requirement is very important for the proof of what we will call the Riccati equation later, times u. And intuitively, the x transpose qx part penalizes state deviation, whereas the utru part penalizes control effort. From this equation, even though it's pretty simple, the idea behind how this encodes essentially cost is not very clear. In fact, before we show how the cost functional introduces state and control input cost, let us make an intuitive example. Let us suppose that a person needs to fly from Germany to Mexico. Let us present three parameters, which are pretty realistic when someone wants to book a flight. The first one is cost. The second one is speed of the flight, including the time the person will have to spend in layovers. And the third one is how likely it is for the person to lose money due to problems occurring with the platform he bought the ticket from. The idea is the following. We want to encode a parametric way to encode how much we want to lean on any of these parameters, sort of like a scroller in a mobile GUI app. One way would be with the following metaphorical formula. The reason why we square the terms is intuitively because we want to equally penalize deviations from the desired strategy, both from the left and from the right. We will now see why the quadratic terms have been chosen, other than the reason specified before. In particular, quadratic terms do three important things. The first one is they penalize large deviations more heavily than small ones. The second is they're symmetric. Positive and negative deviations are treated equally, and we just said that before. And the third one is they produce a convex cost function, guaranteeing a unique global minimum. Of course, in the graph we just shown, we use the parabola, which is a very simple example. We could say one-dimensional example of a quadratic. But in the LQR generally we're dealing with vectors and matrices. Now let's see for each part of the cost functional what does it encode intuitively. The x transpose qx part in particular is essentially state energy. So for example, if we set the matrix Q to be the identity, then of course we get that the term becomes just the norm of x because it's x transpose times x, which is the Euclidean distance of the state vector. And ignoring the control part, or for example setting also the matrix R to the identity, and considering an enlarged vector of just x and u together, in that case the cost function just becomes the L2 norm squared. In this case, which is not really of that much use because every single component, if we set Q equals to the identity of the state vector, is penalized equally, essentially just stabilizes the system but does not prefer any state over the other. So all of them are penalized equally. Sometimes, however, we're interested in scaling certain states higher. For example, let us say, for the sake of example, in a 2D draw model, which has a pose given by x, y, and an angle theta, we could maybe say the component relative to the angle should be higher. In this case, in Toodle, we were saying to the controller, this state matters more, so fix it more aggressively. On the other hand, the term UTRU, which is the transpose of U times R times U, represent how expensive the control is. So essentially control effort or control energy. A large R means that control is expensive, that actuators are limited, and that we prefer smooth and gentle inputs. Whereas a small r, and by the way, by small and large, we should, of course, here we're talking about matrices, and we're not talking about a specific ordering relation on the set of matrices, but rather we are usually having the assumption that these matrices be diagonal. So in this case, we're talking about the size of the coefficients. So a small r means that we're willing to use aggressive control and that fast stabilization is more important than energy. In fact, if a system stabilizes too slowly, we can decrease r in order to allow a more aggressive control to apply. So the core insight is essentially LQR does not minimize state error alone. It does also not minimize control effort alone, but it minimizes the weighted combination over time. Mathematically, it balances performance and effort, and this balance is encoded in the matrix Q and R, which the user, of course, they're user defined. We're gonna choose them essentially. Now, let us go and actually see into detail the formulas that we will use. And essentially, the optimal controller is the following linear state feedback, which is given by U equals to minus kx, where k is the matrix given by r to the minus 1, B transpose times the matrix P, where the matrix P is a solution to the algebraic Riccati equation, which is the following matricial equation. This equation is usually solved numerically, for example in MATLAB or Python, and we should note that the sign convention of this coefficient can vary depending on the elaboration method we're using. For example, in MATLAB it is given with the convention we gave in the video, but in Python it's given with the opposite sign convention. Let us now prove the formulas we just presented, including the Riccati equation. The Riccati equation can be proved starting from the Hamilton Jacobi Bellman equation, which is the following. Intuitively, this equation says the following. The control needed in order to optimally stabilize the system is the one that minimizes the immediate instantaneous cost, which is essentially the x transpose qx plus u transpose ru part, plus the immediate future cost, which is the part where we see the gradient of the j star, which is the optimal functional, times ax plus bu. In this case, since we consider a linear time invariant system, the immediate future cost part does not include also a projection in the future due to a change in time, but only a projection in future due to dynamics, which is the part we saw with the gradient with respect to x of the optimal cost j star. We choose the optimal cost to go function j star to be quadratic, so we can write it as x transpose p x, where p is a symmetric and positive semi-definite matrix. At this point, we focus on the part of the minimizing expression that actually depends on u, which is the control input, and we're gonna call that part phi of u. And what we get is the following expression. Firstly, we know that the gradient of j star with respect to x is just 2x transpose times p. And thus we can write the phi of u as just u transpose ru plus 2x transpose p of b of u. And by grouping together the second term, we can just write that as u transpose ru plus 2 times b transpose px, everything transpose, times u. A simple calculation shows that the Hessian of this function is 2 times r, which, as a consequence of the initial assumption that we made at the beginning of the video, that R is a positive definite matrix, it is a positive definite matrix. But we know that a definite positive Hessian implies that the function is strictly convex. And it is a well-known fact from multivariable calculus that the minimizer for a strictly convex function can be found with the first order condition, which is given by setting the gradient of the function phi, which depends on u, so the gradient with respect to the vector variable u equal to 0. Thus, we take the gradient of phi of u and set it equal to 0, which yields the following equation. By taking the transpose of the expression and dividing both sides by 2, we get the following. But P and R are symmetric, and so we can write just the transpose of R and the transpose of P are just R and P. And by solving for U, we get the following expression, which is exactly the formula that we presented before for the controller. Now, to get the Riccati equation, we simply plug this back into the Hamilton Jacobi Bellman equation, which yields the following chain of equations. This is precisely the Riccati's algebraic equation, which we saw earlier. But as we can see, we have the 2pa term, which is not exactly what we saw at the beginning. So all we have to do is a little bit of algebraic manipulation of that term, which is pretty basic matrix algebra. So recapping, the LQR control provides guaranteed stability if the system is controllable and a globally optimal solution for linear systems. LQR in particular, as we said at the beginning of the video, can be used in various types of actually real-life problems. One such application is in robotics, especially with drones, and one application of the LQR is to make a drone, a three-dimensional drone, stick to the trajectory which we produce with path planning algorithms. And the way we do it, since the 3D drone is not linear, we first linearize the model around this trajectory, and then that procedure yields, it's pretty easy to see, an LTV system. And once we have LTV system, we mentioned in this video that LQR also works for linear time varying systems. But for example, the Riccati equation becomes a differential equation, so it's a little bit different, but the procedure is pretty much the same. In this case, let me know in the comments if you would like a video on how LQR changes for LTV systems soon. And another application of the LQR, in this case we're talking about the LQR we saw in this video, so the LTI LQR, is in the problem of hovering. In this case, since the hover point of a drone is an equilibrium point, linearizing the system around that point will yield a linear time invariant system, and thus the LQR we studied in this video applies. Having said this, I thank you for watching the video, and I hope to see you soon on the channel for more.